All right. Well, we've been talking about vectors. So back to vectors. We're almost done talking about what we need to. So far we've been talking about if you have a coordinate system and you have a vector given as a magnitude and a direction, how to figure out the components of that vector. And I said that the reason that you express a vector in component form is because calculations are easier. So now I'm going to give you the 3 calculations involving vectors that we're going to use in this class. So once you have a vector expressed in components, or 2 vectors in some cases. So let's say once you have your vectors expressed as components, here are 3 important calculations. The first one is adding 2 vectors. So if you have a vector AB and you're adding it to a vector CD, the way you do that is the sum of these 2 vectors is also going to be a vector. And the x component of this output vector is just going to be the sum of the 2 x components. And the y component of the sum of these vectors is just the sum of the 2 y components. So for example, if you have the vector 5, -2, and you're adding it to the vector -3, -6, 5 plus -3 is +2. -2 plus -6 is -8. Okay? The physical meaning of this, or maybe physical is the wrong word, maybe graphical meaning or something, but if you're adding two vectors like this, think of the input vectors as legs of a trip, and the output vector, the answer, the sum, vector, is the shortcut of the trip. So for this example here, a trip, you'd start somewhere, right? So I'll just choose this point. You take one of those vectors, it doesn't matter which one. And now you're at this intermediate point where you have lunch and check out the amusement rides or whatever. And then from there, you do the second leg of the trip. And the sum is the shortcut of that trip. So now you call back to your friend like, oh, don't do this. It's not worth stopping at that place for lunch. Just go straight from here to here. Okay, so that green is the sum of those two circled vectors. And mathematically, that's what you get when you use this, this way of calculating it. Okay? The second calculation that we're going to do is multiply a vector by a number. So if you have a number c and you're multiplying it to the vector ab, the vector you get out has c just multiplied to both components. So the x component of the output vector is c times a. The y component of the output vector is c times b. Okay? And the physical meaning of this is the length of the output vector is c times the length of the input vector and if c is negative, it just flips the which side is the tail and which side is the head. Okay, so as an example, if you multiply -3 times the vector 2, 1, what you get out is the vector -6, -3. 2, 1 looks like this. So if there's your coordinate system, you know, plot the point 2, 1. And then draw the vector that goes from the origin to that point. So that's the vector 2, 1. -6, -3. One, two, three, four, five, 6. 1, 2, 3. So this would be this point. Draw the vector that goes from the origin to that point. So that's -6, -3. And what happened is when we multiplied the black vector by -3, we got a vector that's 3 times as long in the exact opposite direction. Okay? Any questions about either of those yet? And the last calculation that we'll occasionally have to do is to calculate the magnitude of a vector. So a lot of times you'll be given the magnitude of a vector to start with, and you'll have to calculate the components. That's what we've done so far. But there are some cases where what you'll be given is the components of the vector, and then you'll have to calculate the magnitude. So to do that, So if we call this vector u, that's equal to, let's say, AB, okay? The notation for the magnitude of this vector is, write it as like the absolute value of a vector. That's what that means. And the magnitude of this vector is a squared plus b squared square root. That formula probably looks familiar. Remember what that formula is? That's the Pythagorean theorem. And if you think about, so the physical meaning of calculating the magnitude this way physical. Remember that the meaning of, so if we have a coordinate system like this, okay, and we have a vector like this, the meaning of the components, this is the x component, and this is the y component. Okay, so like this black would be the vector u. This would be the x component of u. This would be the y component of u. Let me use the notation I did before. So this is A, this is B. Well, now you can see why the Pythagorean theorem gives you the magnitude of that vector. If the components are A and B, they form a right triangle with the vector itself, and the magnitude, the length of the vector itself, is the length of that hypotenuse. Okay? So yeah, this is just the Pythagorean theorem. Okay, let's do an example problem that I think there's at least one problem in the homework that you'll have to do that's sort of like this. So let's say we have two vectors. So let's say our vector A is equal to 4, 1. No, I'm sorry. Let's do this differently. Erase that. So let's say that A is equal to a vector like this that has a length of 10 and makes an angle of, let's say, 20 degrees with the horizontal. And B is a vector with a magnitude of 20 that makes an angle of 40 degrees with that horizontal. And we want to calculate first what's A plus B in a coordinate system like the one we're used to. And then let's do that first, and then we'll do another coordinate system. But hopefully this will sort of show you how all these pieces work together. So the first thing we're going to have to do is calculate the components of each of these two vectors in this coordinate system. A looks like this. B looks like this. We know that this angle is 20 degrees and this angle is 40 degrees. Okay, so for the components of A, What's the counterclockwise angle from the positive x-axis to this vector here in the first quadrant? 20, yep, that's right. So this is just going to be the magnitude of that vector, 10, times the cosine of 20 degrees, and then 10 times the sine of 20 degrees. Do this calculation. Make sure your calculator's in degrees and not radians. And this comes out to be 9.40, 3.42. And now the vector b. That is a magnitude of 20. So we're going to multiply 20 times cosine and sine of something. What's the counterclockwise angle to get from the x-axis to this other vector in the second quadrant?
140.
Yeah, 140, because you can see that if you went all the way from the x-axis to the negative x-axis, that would be 180. But then you'd have to backtrack 40 degrees. So 180 minus 40 is 140. Okay? So this is going to be 20 times the cosine of 140, 20 times the sine of 140. And that comes out to be 7.32, 15.32.
I got negative 15.8.
Yeah. Negative 15.32, and then positive 12.86, right? Now it's just a matter of adding these two, so A plus B is equal to 9.40, 3.42, plus negative 15.32, 12.86. And so you get 5 point, what's that, 5.92?
Yes.
Negative. And then 14, positive 14.28. Okay?
Would be 16.28.
Yes. Okay? So now what about the meaning of that? So what's the meaning of that vector? Well, if you draw the coordinate system again, and draw out that vector. So let's go negative 1, 2, 3, 4, 5, 6, and then positive 1, 2, 3, 4, I'm going to run out of room. 5, 6, 7, 8, 9, over here somewhere. So this is going to give you a vector like this. And the effect of that vector is there are two original vectors, and this is how vector addition works. Okay? Okay, so now for part B, let's use the same two starting vectors. But this time you're going to calculate their components in a coordinate system like this, with the x-axis up and the y-axis to the left. Okay, so calculate the components of A and B in this coordinate system. And then once you have those components, then add them together. Okay, so take a few minutes and see if you can work through that. Talk to each other or talk to me if you get stuck, and then I'll go through. What's the counterclockwise angle from the x-axis to this vector here on the, in the upper right?
290.
Okay, so you'd go from the x-axis 90, 180, 270, plus 20, so yeah, 290. Okay, you could also use negative 70 and you'd get the same thing. Okay, you can go clockwise and write it as a negative angle. So for the first one, A, we have 10 times cosine of 290 and 10 times sine of 290. And that comes out to be positive 3.42, negative 9.40. And then for B, what's the counterclockwise angle from X to that vector?
50 degrees.
That's right. It would be 90 to get to the y-axis, then backtrack 40, so 50. So B is equal to 20 times cosine of 50, 20 times sine of 50, and this time you get 12 point, what was it, 86, and then positive 15.32, right?
Yes.
And now you just add up those components. A plus B is equal to 3.42, negative 9.40, plus 12.86, 15.32. And you get, what was this, 16.28?
Yes.
And this one was, what was this one, 5.92?
5.93.
5.93. Okay, so that's just numbers until you sort of visualize what that vector is. So let's do that. So our x-axis is up. Our y-axis is to the left. And we want to go 16.28 in the positive x direction. And 5.93 in the positive y direction. And so you get a vector that's like this. And, you know, obviously I'm just doing this freehand and everything, but maybe you can at least believe that if I really measured this stuff out, used a protractor, used a ruler, I would have gotten exactly this same vector back, even though the numbers are different, reflecting the different coordinate systems. Okay? So it's the same vector sum as in part A.
I have a question. So why, like, we got, I think I did 90 plus 40,
Mm-hmm.
and I got 140. Oh, 130.
Oh, yeah, right. So, well, this angle, since this one is 40, this one would be 50. You see that? And so you could go 90 plus 50 and get the same thing. Because it's 90 degrees between every pair of coordinate axes. Any other questions? Okay, so now the idea is we know what we need to about vectors. Now we're going to use vectors to define our two-dimensional kinematic quantities. So now we can use vectors for 2D kinematics. Okay, well, we have to define 3 different vector quantities. So we have to define a position vector, a velocity vector, and an acceleration vector. Okay, so first, the position vector. Do you remember way back when we talked about position in 1D kinematics, what we had to define before we could assign a number to position? There were 2 things we had to define. We hadn't defined the times yet.
Starting point in the direction.
It wasn't a starting point, it was a 0 position, that's right. So we have to define a reference, something we're going to reference everything to, and then a positive direction. So before you can represent an object's location with a vector, you have to choose 2 things. It's sort of like the 2-dimensional equivalent of a 0 position and a positive direction. Can anyone think what those might be? It's sort of a hard question. So before we can represent an object's location with a vector, we need to choose, well, what would you think of as the 2-dimensional equivalent of the 0 position?
In real life or on the graph?
In real life. It's the coordinate system origin. So now instead of thinking of putting a ruler down on the ground or painting a number line on the ground, you can imagine painting a coordinate system in whatever plane the motion is happening in. So coordinate system origin. And this is like the 1D 0 position. And you also have to choose a coordinate system orientation. Coordinate system. So you also have to choose a coordinate system orientation, and that's like the 2D equivalent of choosing a positive direction. Once you've chosen those, The position vector is the vector from the origin to the object's location and there's an easier way to think of it. It's just the coordinates of the object. So the position vector is just the coordinates of the object in that coordinate system that you chose. The units for position. So vectors don't have their own units. They're just kind of like a mathematical object, the same as a number is. So you can have a vector represent things with all sort of units. The units for 2D are going to be all the same as the units were in 1D. So the units for position are going to be length. And that means the SI units for a position vector are going to be meters. Okay? Okay, so if you have, this is just like a quick little example, but if you have a coordinate system like this, so here's 1, 2, 3 in the x direction, 1, 2, 3, 4, these are negative in the y direction, and your object is here. Okay. The position vector would be this. I mean, remember, a vector always is just a magnitude and a direction. But since we represent vectors with components, that position vector would just be the coordinates of that point, which would be +3, -4, and the units are meters. Okay? So next we have to think about velocity. Fundamentally, the velocity means the same thing that it did in 1D. It measures how quickly the position vector is changing. So the velocity vector, you sort of want to think of this as two separate things, and we talked about it this way in 1D also. We talked about the absolute value of the velocity was the speed, and then the sign of the velocity told you the direction, okay? The magnitude of the velocity vector, the length of that arrow, is the speed. And the direction where that arrow is pointing is the direction the object is moving at that instant. The units of velocity are the same as they are in 1D. So it's units of length divided by units of time. And that means that the SI units for velocity are meters per second. And there are three things that you need to remember, keep in mind about velocity. So notice. The first one is you often need to calculate velocity components from a speed and an angle. So you often need to calculate the components of the velocity vector from the object's speed and angle. So an example of that, you might have a problem that says the object is launched at 20 meters per second, 30 degrees above the horizontal. Well, to picture that, choose your coordinate system. You know that your vector has a magnitude of 20, and it makes an angle of 30 degrees with the horizontal. Now go through the steps of calculating the vector components, and your velocity vector at that instant will be 20 times cosine of 30 degrees, 20 times the sine of 30 degrees, and you'll get 17.32 and then 10. And it has units of meters per second. Okay, so that's the first of these things to keep in mind. The second one is when an object is dropped. This came up in 1D also. The velocity vector at the instant that it's released is the velocity vector of whatever it's dropped from. So it's the velocity vector of what it's dropped from. Okay, so for example, let's say that a ball is dropped from a car that's moving at 20 meters per second. What's the velocity vector of the ball when it's dropped? you know, a little after it's dropped, gravity's going to change it, whatever other stuff is going to change it. But at the instant it's dropped, what's its velocity vector? Well, it's dropped from a car that's moving 20 meters per second, and assuming that the road is flat, there's the velocity vector of the car at the instant the thing is dropped. So in the coordinate system, what are the components of this vector? Remember that you can always think of the components of the vector as the coordinates of the point if you put the coordinates of the head if you put its tail at the origin. So what are the coordinates of the head there? Yep. So this is just 20, 0. And that's the velocity vector of the ball at the instant you let go of it out of the window of the car. Okay? Or inside the car. I mean, if you're in a car and you let go of a ball, to you in the car, it looks like it just falls straight down. But to somebody who's, say you have a glass car, you know, somebody watches you from the side, to them it looks like what this ball looks like, if they're ignoring the rest of the car, is that it starts out moving with the speed of the car this way, and then gravity makes it fall down to the ground, and it follows a parabolic path. Any questions about velocity? Okay, and then the last one we have to talk about is accelerate. Oh no, there's one more thing you have to notice. For a coordinate system with the y-axis pointing up, an object reaches the highest point in its motion this is for projectile motion and free fall. It reaches its highest point when the y component of velocity is equal to 0. Not the whole vector. Okay, so in 1D, when you launched an object up into the air, it got to the highest point when the velocity was equal to 0. Now in 2D, when an object gets to its highest point, the x component doesn't have anything to do with it. The only thing that matters is the y component. Okay, so, and I think I mentioned this before, but picture it this way, and I think this is a pretty effective, like intuitive, like if you think about this, you'll understand why this is the case. So imagine, a baseball player, a pro baseball player out in the outfield, possibly a gorilla. Okay, anyways, so here's this outfielder and he throws this ball as hard as he can, okay? And it's gonna fly in the air, say 400 feet, you know, a long way. He's throwing it at close to 100 miles per hour. if you know where the highest point is that the ball is going to reach, the question is, do you want to set up a ladder there? There's you. I didn't have room to draw a body. Do you want to set up a ladder so that that ball is aiming right at your head at the highest point, you know? If the velocity vector was equal to 0 when this ball reached the highest point, then this ball would slow down, slow down, slow down, and right as it got to the back of your head, it would be at 0 velocity. You wouldn't even feel it. It would just barely touch your head, and then that would be it, okay? I mean, imagine standing in the middle of a baseball diamond and having someone throw a ball 100 miles per hour at your head. There's no way that that's how it really works. You know what I mean? So don't do this. What's happening is when this guy throws the ball, the x component is almost 100. It's, say, 98 miles per hour. The y component is, say, 2 miles per hour. Okay? It reaches the highest point when the y component is 0, but the x component is still 98 miles per hour, and it would hurt very, very badly. Okay? Okay, so now that's it. Now we have to talk about the acceleration vector. So the velocity is measuring how quickly the position is changing. The acceleration is measuring how quickly the velocity is changing. How quickly the velocity vector is changing. One important thing about the acceleration in 2 dimensions. So this is like a key fact about acceleration. In 1D, acceleration means the speed is changing, and that's the end of the story. The thing can either speed up or slow down. If it doesn't do either, the acceleration is 0. In 2D, there's actually an entirely different thing that acceleration can do. So in 2D, acceleration makes the speed change. And or the other thing that it does is it makes the object turn. In 1D, there's no such thing as turning because you're confined to go along this line, you know. So that's a new thing that we have in 2D that we didn't have in 1D. And to think about how this works, you know, in space movies, they always show astronauts training on these things where they sit in like a chair and spin around. You know what I mean? You know what I'm talking about? No? Okay, let's see. When I was a boy, astronaut movies were more common, I think. But, so anyways, they put him on this thing that can spin around. And it's a way of getting used to very high G accelerations. Okay, well, how does it work? Once it gets up to speed, the speed isn't changing at all as the astronaut goes around, So how's it accelerating? Well, the answer is that the astronaut is turning really fast to go around this circle. And so even though the speed is constant, there's a big acceleration, okay? So remember that in 2D, just because the speed is staying constant doesn't mean the thing has zero acceleration. In 1D, it would mean zero acceleration, but not 2D, okay? So this example shows constant speed, but there's acceleration because it's turning. Okay, the units for acceleration, the same as 1D, everything's the same as 1D, is length units over time squared. And so that means that SI units are meters per second squared. And there's one more thing that I want you to notice. In free fall and projectile motion, if you choose your y-axis up, which we usually will, not always, but usually, gravity accelerates things down, and so the acceleration is always 0 for x, negative 9.81 for y. And that just means 9.81 meters per second squared, pointing down. Anybody have any questions about acceleration? We'll spend some time in lab and some time in class talking about interpreting acceleration in 2D. It's a hard thing to visualize, but I'll give you some things to think about to visualize it. But before we get into that, we're going to work on the constant acceleration equations in 2 dimensions. And it's going to be very similar to what we did in 1D. But now we're going to be able to do more complicated motions. So the constant acceleration equations in 2D. And to remember these, all you have to do is remember the 1D constant acceleration equations. I mean, you don't have to remember these. They'll be on tests given to you and everything. But I just want you to notice that the form of these is exactly the same as the form of the 1D constant acceleration equations. The only difference is for the things that are vectors, position, velocity, and acceleration, there's going to be components in all these things. So it's going to look a little messier, but it's the same idea. So remember in 1D, we had an equation that said VF is equal to VI plus ATF. So now we're going to have 2 of these. Let me write it twice. So VF is equal to VI plus a TF. And the only difference is now one of these two equations has all x components, and one of them has all y components. And remember, t isn't a vector, so it doesn't have any components at all. It's only the position, velocity, and acceleration ones that have components. Then the second equation said PF is equal to PI plus VI TF plus 1/2 A TF squared. I'm going to cheat. And so one of these is all x components, and one is all y components. And then the last one says 2a times the quantity PF minus PI is equal to VF squared minus VI squared. And we have one of these that has all x components. And one that has all y components. Okay, well, let me give you a set of 4 steps for solving these. You're going to see it's very similar to the steps in 1D problems. And we won't have time to do an example problem, I don't think, today, but I'll give you the steps, and then next class we'll do some examples. So this is general steps for 2D constant acceleration problems. So the first one is you have to choose an origin location and a coordinate system orientation. And then you have to choose an instant for time equals 0 and an instant for time final. And just like in 1D, you choose those based on where you have information or where you're trying to calculate something, when you're trying to calculate something. After that, the second step is list out what variables you know and what variable you're trying to find. Okay, well, unfortunately, the list of possible variables is almost twice as long now because of the x and y components, but you can still just go through the list. Well, I'm going to write it like this. The list is TF A, which is a vector, so that's an x and a y component. PI, again, that's an x and a y component. PF, VI, and VF. TF is just a single variable. Each of the other ones is two variables, an X and a Y component. So that's 2, 4, 6, 8, 10, 11 total variables. Third, look for an equation. All of this stuff, the reasoning is exactly the same as it was in 1D. Look for an equation that has the variable you want and every other variable in the equation is known. Every other variable in the equation is known. And then the last step, you don't always need this, so I'm going to put it in parentheses. But if no equation works, find an equation that lets you solve for time final. So solve for TF and go back to step 2. Okay? Anybody have any questions about that? All right, well, let's call it for today, and then on Thursday, I'll just, for the whole class, we'll just do example problems.